Hi everyone. In the second part of Learning Unit 5, Acid-Base Titration, we are going to look into the aspect of polyprotic acid titration with strong titrant and polybasic base titration with strong titrant. So in the case of polyprotic acid and polyprotic base, we're not going to do the calculations involved, but instead we are going to look at the design and the curve for both polyprotic acid and polybasic base. When one titrates a polyprotic acid with a base, there is an equivalence point for each dissociation of the H plus ion in the acid. As we know that when we talk about a polyprotic acid, we are talking about an acid which has more than one proton to be dissociated. Okay, so in the case of the examples we're looking here, H3PO3, we are looking at 3 H plus ion to be dissociated. Which will dissociate first is depends on the Ka. H with the higher Ka will dissociate first compared to the H plus ion with lower Ka. So if we have 3 proton to be released during titration process, there will be 3 equivalence point. Okay, so what we see here is that we have one equivalence point for the first proton here, and the second one here, and the third one here. Okay, so this is what happened when we have a titration between a polyprotic acid with a base. Right? And because we are dealing with an acid sample as our analyte, we start with an acidic pH. So you will have the curve running from the lower pH and ending with a higher pH at the end of the titration curve. If you look at the 3 equivalence point for the 3 proton released by the polyprotic acid, which is H3PO3 here, you see that for all of the 3 titration curve, they have their own inflection point. Okay, so if you look at another case where we have a titration of polybasic base, let's say you have a titration of Na2CO3 with HCl. In this case, Na2CO3 is the polybasic base. Okay, so from this example, you can see that it starts with a higher pH, which is pH 11, and ends with a lower pH. This is because you start with a base as your analyte. All right, and you will have several equivalence point here. If you look at here, because you are dealing with a polybasic base. As I have mentioned earlier, we're not going to have any calculation details for the polyprotic acid and the polybasic base titration, but instead you have to recognize how the titration curve will look like for both of the polyprotic acid and polybasic base titration. Now let's move to the endpoint determination. Okay, so we are going to look at how we select and evaluate the endpoint. Again, this is some revision on what we have discussed in the first part of this learning unit. Equivalence points occur when we have a stoichiometrically equivalent amount of analyte in titrant that reacts during the titration, meaning to say that we have the similar number of mole for both acid and base at equivalence point. So this can be calculated earlier if we have the important information. Let's say we have information on the concentration and volume of acid and base, we can calculate the equivalence point. And in the case of titration between strong acid and strong base, we already know that the pH at equivalence point is always 7. And for titration between weak acid and strong base, and weak base and strong acid, we can calculate the equivalence points using this concept. Okay, this is because at any equivalence points of titration, we have a stoichiometrically equivalent amount of analyte and the titrant. Okay, because this can be calculated, it is a theoretical value. It is considered a theoretical value. And another revision on endpoint. Endpoint for a titration is determined experimentally, and it represents the analyst's best estimate of the corresponding point. So when we talk about the endpoint, it is the nearest or the most the most closest value that we can get, which can be physically visualized by titration, okay, by using indicator. So it should be as close as possible to the equivalence point, and it's important to select a proper indicator for each of the endpoint required. Okay, so any differences between the endpoint and the equivalence point is a source of determinate error, as we have seen in previous discussion, that we have determinate error equals to the endpoint, which is the experimental value of a titration, and minus the equivalence point, which is the theoretical value of the equivalence point. For most acid-base titration, the inflection point or the greatest slope in the titration curve very nearly coincides with the equivalence point. So if you look at this figure here, the titration curve figure, you look at the inflection point. What is meant by inflection point is the area here when you have the equivalence point. Okay, so the main limitation to use a titration curve to locate the equivalence point is that an inflection point must be present. But sometimes an inflection point may be missing or difficult to detect due to the small value of acid dissociation constant Ka. So if you will look at the figure here, the figure shows that the titration curve for a weak acid with a strong base titrant here, the inflection point is visible if you have Ka larger than 10 to the power negative 9, but is missing when you have Ka at 10 to the power of negative 11. Okay, so when you have pKa here, pKa is 11. So this means that you have a lower Ka. This one is lower Ka. So if you look at here, you cannot determine which one is the equivalence point because you don't have the inflection point. Okay, whereas for let me erase this one first. Okay, where else? If you look at pKa 9 here, meaning it has slightly higher Ka compared to pKa 11. You look at here, you still have your inflection point where you can determine the equivalence point. The same goes with the green line here, red one, purple, and aquamarine line here. Okay, so from this inflection point, you can determine your equivalent point. Okay, but for acid with very low Ka, it is difficult for you to determine the equivalence point from the inflection point because it is not visible. It's not even having, you know, which part of it is, can be determined as the equivalence point. We don't know which part because the inflection point is not visible. Another situation where an inflection point is missing or difficult to detect occurs when the analyte is a multiprotic weak acid or base, which successive dissociation constant are similar in magnitude. Just now we have discussed about the shape of uh, the titration curve for polyprotic acid and polybasic base, which they have more than one inflection point. For example, if they have 3 proton, they will have 3 inflection point. If they have 2 hydroxide ion, they have more than one, means 2 inflection point. But in the case of multiprotic weak acid or weak base, you may have the problem where both of these inflection point, they are very close to each other. Let's say if you look at this green curve here, you don't know which one is the equivalence point because for this case, they are very close to each other and it's very confusing if you want to determine the equivalence point solely based on the titration curve. However, for the pink curve here, if you look at the inflection point on the pink curve, it's very obvious and you can determine your equivalence point for both of the proton involved in the acid. Okay, but sometimes we have difficulties to determine the equivalence point if we have multiprotic weak acid or base which have successive dissociation similar to each other. Okay, in general, inflection points are distinct when successive Ka differs by a factor of at least 500. Okay, so if we have less than that, it will become like this titration curve whereby it's difficult to determine the equivalence point. Because there are some difficulties for us to determine equivalence point through titration curve, there is an alternative way that we can use, which is indicator. Okay, by using indicator, we can determine the most closest endpoint, which is the closest to the equivalence point. Okay, so what is indicator? Indicator are acid-base indicators are highly colored weak acid or bases. Okay, so during a titration at the endpoint, they will change color from color 1 to color 2. Okay, and for some indicators, they may have more than one color transition. For example, if you talk about metal red, it can change color from yellow to orange to red. Okay, and for some indicators, they can even be changed to colorless. For example, the starch, it can change from blue color to colorless, and phenolphthalein can change from colorless to purple. Okay. So during an acid-base titration, the indicator acts as an additional weak acid or base. So you have to be careful when you want to use the indicators for your titration, especially when you are dealing with titration between weak acid or weak base. This is because if you have indicators which has Ka or Kb near to the weak acid or weak base in concern of your titration, it will cause interference during the endpoint determination. Okay, so you have to take note that the indicators must be weaker than the species being determined in the titration, and it must be present at very low concentration, so it will not interfere with the normal titration curve and the equivalent point. Another important properties of an indicator that should be considered when choosing an indicator for your titration is that it must give a sharp and distinct color change at the required endpoint. So this is some figures to support the things that I've mentioned just now. When you have too much indicator present in your analyte, you will change the inflection point. Okay, let's say you have the normal titration curve as in blue curve here, but when you add too much indicator, the inflection point will change as in the red curve. Okay, this shows that you add too much indicator. Okay, because the it's supposed to be like this, whereby you add a little indicator just to show where your equivalent point is. Okay, so when you select an indicator, it should be as small amount as possible, so it can produce a color that we can observe at the endpoint. Okay. The indicator should not significantly start to undergo a color change until we have passed the equivalence point. I think we have also discussed this during learning unit 4 when we talk about indicator. Again, it is emphasized that when you choose an indicator, it should show color change only right after passing the equivalence point. For example, in any acid, a strong acid and strong base titration, we know that the equivalence point is at pH 7. So we should choose an indicator that change color not below pH 7, but slightly above pH 7. Okay. All right. The average analyst will observe a color change when about 1 to 10 of the indicator be converted. The pH of conversion for approximately 1/10 of the indicator is starting from, if you start from basic condition, then you have this equation, and if you have start the titration from acidic condition using this equation. Okay, so this is the Henderson-Hasselbalch equation. So under this condition, the transition range for the indicator is pKa plus minus 1. Ideally then, we want our indicators pKa to be 1 unit above the pKa of the acid sample, meaning to say that we want our indicators pKa to be 1 unit above the pKa of acid sample, meaning to say that the Ka of our indicator should be lower than the Ka of our sample. Remember this? Okay, because we don't want indicator with high Ka to interfere with the endpoint visualization. Okay, for bases, it should be 1 unit lower, and we seldom find a perfect indicator, so we should use one that is a minimum of 1 unit away. So this is the list of common indicators used for titration. If you look at the pH range that they serve, for example, cresol red, it can show color change between from red to yellow at pH 0.2 to 1.8, which is very acidic. Okay, and if you look here, methyl red, for example, it changed color from red to yellow at pH 4.2 to 6.3. And here, if you look at the list, we have cresol red, which changed color from yellow to red at pH 7.2. If you look at bromothymol blue, change yellow to blue at pH 6 to 7.6. Okay, so when you want to choose an indicator, let's say you have bromothymol blue and cresol red, if you have a titration between a strong acid and strong base, which equivalence point should be at pH 7, maybe you would like to consider cresol red, because cresol red only change color at slightly above pH 7, which is 7.2. Don't use bromothymol blue for that situation or for that case, because bromothymol blue change color earlier than pH 7, which is pH 6. Okay. In some cases, mixed indicators or by adding a neutral screening dye to an indicator will give a narrower range of pH over which the color change occurs. For example, if you look at the previous table, bromocresol green and methyl orange. If you look here, bromocresol green gives you a range between 3.8 to 5.4 pH range. Okay, and methyl orange gives you pH range between 3.1 to 4.4. However, if you combine bromocresol green and methyl orange as a mixed indicator, you will narrow down the pH range that can be detected for the endpoint of a titration. Okay, the same case goes for bromothymol blue and phenol red mixed indicator. It will narrow down or make the pH range for detection of endpoint smaller. Okay, smaller pH range. So this is example for screen indicator. If you have dimethyl yellow and methylene blue, your pH range this one. If you have methyl red and methylene blue, you have this one, and so on. So the point that I'm trying to convey here is that mixed indicators and screening dye can help to narrow down the range of the pH that can be detected uh, for the endpoint of a titration. Okay. Now, to minimize the determinate error, as we mentioned just now, determinate error is the difference between the experimental value or the endpoint detected in your titration process and the theoretical value, which is the equivalence point calculated from the information that you have. Okay. So to minimize the determinate error, an indicator's entire color transition must lie within the sharp transition in pH occurring near the equivalence point. For example, phenolphthalein is an appropriate indicator for the titration of acetic acid and sodium hydroxide. Okay, whereas bromothymol blue is not suitable since it changed in color begins before the initial sharp rise in the pH, and as a result spans a relatively large range of volume. Okay, if you look at any titration curve, the equivalence points is always at the middle of the of the curve here, of the stiff curve here. Okay, all right. But if you use an indicator which can detect early the end, sorry, let me repeat that. If you use an indicator which give color change before the equivalence point, it is not accurate. Okay, so this is why you should choose an indicator which can shows the color change at suitable pH range. It must be slightly after the pH equivalent pH. Okay, all right. So about titration error, excess titrant must be added to the sample to convert the indicator. Okay, so the effect can be minimized by titration of one or more blank samples. So when you do titration, it's important for you to have blank sample in order to minimize the determinate error. So blank sample can be done by using same solution volume and identical amount of indicator. Okay, the blank amount can then be subtracted from the total amount of titrant needed. Okay. Another type of titration error is the indeterminate error. Each person will differ in how well they can observe a specific color change. So running a blank will help minimize the problem. Okay, we can also prepare a reference solution. A blank adjust to the exact pH for the desired endpoint. Okay, whether you will use a blank or a reference solution. So this will help to decrease or reduce the indeterminate error. So indeterminate error is caused by the way different person see or observe the color change. Okay. Besides using visual indicator, endpoint can also be determined by using auto titrator. Okay, so using auto titrator, pH is measured by electrodes immersed in the analyte solution. So from the electrode, the change in pH are computed. Okay, so the endpoint is where delta pH and delta volume is maximum, first derivative, and uh, you have change here as the second derivative. Okay, so this is how your titration curve will look like if you use auto titrator. It's easier compared using indicator. Okay, these are some of the applications of titration process. Titration process can be used for inorganic analysis. Um, Inorganic acid and bases too weak to be analyzed by an aqueous acid-base titration can be analyzed by adjusting the solvent or by indirect analysis. Okay, indirect analysis here is what we have mentioned in previous part of this lecture, which is the back titration. And it is basically two-step titration, whereby you have excess of one solvent and then you recalculate the mole and you have the answer or the you know the endpoint that you want. Okay. Right, let's say for this example, you are titrating boric acid H3BO3 with NaOH, okay, whereby this titration is limited by boric acid's small Ka. The Ka is very small, which is 5.8 times 10 to the power of negative 10. You remember what happened if the acid has very small Ka? We cannot visualize the equivalence point from the titration curve because it has no inflection point. Okay, so in order to overcome this problem, you can add another chemicals. Okay, So in this case, Ka will increase to 1.5 times 10 to the power of negative 4 when mannitol is added to the solution. So this will result in a sharper endpoint because of the higher Ka, okay, and a more accurate titration. Okay, so acid-base titrimetry or standard method for the determination of alkalinity, acidity, and free CO2 in water and wastewater analysis. So these are some of the quantitative applications of acid-base titration. Okay. Okay, here are some other applications or quantitative applications of acid-base titration. The most common one we will be using whether as a chemist or people working with food or people working with plants is Kjedahl method, okay, which is a method to determine protein content in a sample. Okay, so Kjedahl method has its own standard procedure. Okay, so normally in Kjedahl method, your sample is digested with mercury oxide as the catalyst, K2SO4 and concentrated H2SO4, which is to convert nitrogen to NH4. Okay, so the solution is boiled until it turns clear and for another 30 minutes. Okay, after it turns clear, it is continued boiled for another 30 minutes, and after cooling, water and 4% weight to volume K2S are added to remove the mercury oxide catalyst. Then you add sodium hydroxide to convert ammonium to ammonia, and you distill the ammonia into a collecting flask containing a known amount of standardized HCl. So after the distillation is complete, titrate the excess HCl with a standard solution of sodium hydroxide using methyl red as visual indicator. So the analysis of protein is based on a determination of percent weight to weight nitrogen in the sample. So different protein will have different amount of nitrogen. The experimentally determined percent weight to weight nitrogen is multiplied by a factor to give the percent weight to weight protein in the sample. So basically in this process, in Kjedahl method, you are looking for percent weight to weight nitrogen, and then you multiply it with a factor depending on the type of sample that you have to get the weight to weight percent of protein. Okay, so these are the three main things that you have to understand in Kjedahl method. Okay, so if you are dealing with cereal protein, the factor is normally 5.7. For meat protein, 6.25. For dairy products, 6.38. Now let's look at the example here. You have 0.712 1 gram of sample of a wheat flour. So when you have wheat flour, this is a wheat. So wheat is a cereal protein. Okay. So it is analyzed by Kjedahl method. So what is the purpose of Kjedahl method? To determine the percent protein. Okay. So based on the method explained previously, the method is the same for all sample as long as it is named Kjedahl method. So the method would be the same. So what happened here is that the ammonia formed by the addition of the concentrated base after digestion with H2SO4 was distilled into 25 ml of 0.04977 HCl, molar HCl. Okay, so the excess HCl was then back titrated with 3.97 ml of 0.04012 molar NaOH. So calculate the percent protein in the flour. Although you look at the question, it's very long, but it is simply just a manipulation or a twist of the normal titration calculation. Okay, so the most important concept that you have to understand is that in back titration, you have titration with excess titrant, which later on you have to recalculate it to get how much is the excess of a mole involved in the titration. Okay, all right. From the question, we know that we have 25 ml of hydrochloric acid. We have 0.04977 molar of HCl. Okay. Okay. So when you calculate the millimole of acid here, you have to consider MV. Okay, what is the M? M is 0.04977. What is V? V is 25 mil. So you get millimole. Because you use ml, you get millimole. Okay, so 1.2443. Now you calculate the amount of NaOH. The amount of NaOH is also MV. What is the concentration of NaOH? Concentration is 0.04012. What is the volume? It is 3.97 mil. So you have 0.1593 millimole. So the excess millimole that you have is amount of HCl. So millimole excess, okay, excess millimole. Okay, so you have 1.2443, the amount of HCl minus 0.1593. Okay, from there you get amount of nitrogen as the excess millimole between HCl and NaOH. Okay, it comes from here. Okay. After that, you can calculate percent nitrogen in your sample. Okay, so the first step is to find the excess millimole so that you can find the amount of nitrogen. Okay. The second step is for you to calculate the percentage of nitrogen. So this is the mole of nitrogen taken from step 1 just now. So this is formula mass of nitrogen or molar mass of nitrogen, but not in gram per mole, it's in gram per millimole. That's why you see here is 0.014 gram. Okay, that's because you have convert gram per mole to gram per millimole. Okay, so divided by the amount of sample, the mass of sample, 0.7121, which is given in the questions, and you multiply with 100%. So you get the value 2.1341. If you want to calculate the percent of protein, you go to step number 3. Percent protein is percent nitrogen times factor. Okay, percent nitrogen times factor. So the percent nitrogen that you get from the calculation just now is 2.1341, and factor for cereal protein is 5.7. So you just multiply them and you get the final answer. Percent protein is 12.16. Right? Easy, right? So if you look at this question exercise, it is also the same approach that you can use. Okay, let's see the question here. We have a sample of cheese. Cheese is a dairy product. So for dairy product, we have 6.38 gram factor. Okay. So we have a mass of sample 0.9814. And then we have HCl, volume 50 and concentration 0.1. So you can calculate millimole HCl from here, and then millimole of NaOH from here. Okay, NaOH. So this is the first step, which is for you to calculate nitrogen. Nitrogen is millimole HCl minus millimole NaOH. So step 2 is for you to find percent nitrogen. This is step 2. So percent nitrogen, you can find it using this formula just now. You already get the amount of nitrogen times the molar mass of nitrogen in gram per millimole divided by the mass of sample. So that's the second step. And the third step is you already get the value for your nitrogen percentage. You multiply it with the factor, which is 6.38, and you get the answer, 23.1% weight to weight protein. Try to do this on your own so that you can understand the step by step calculation. Okay, so there are many ways to evaluate the acid-base stoichiometry. For example, the first thing that we can measure is the scale of the operation. Okay, the volume of titrant needed to reach the equivalence point is proportional to the absolute amount of analyte present in the solution. So in solution, the smallest concentration of analyte that can be analyzed is approximately 10 to the power negative 3 molar. So methods for titration on a much smaller scale have been developed. So the smallest volume successfully titrated was 20 microliter. Okay. Another point of view that we have to consider for acid-base stoichiometry is the accuracy of method that we want to use. The relative error should be between 0.1 to 0.2%. Okay, and the main limitation or the difference between the endpoint and the equivalence point, which is the determinate error. So this is the main limitation. Okay. Another factor is the precision of acid and base stoichiometry. It depends on the precision with which the endpoint volume can be measured and the precision of the endpoint signal. Okay, under optimum conditions, a relative precision of 0.1 and 0.2% can be accomplished. Okay, so we know that for accuracy, this is the main range, and for precision, this is the main range. Okay, so it's quite good. All right, for acid-base stoichiometry, the sensitivity can be increased by decreasing the concentration of the titrant, or for polyprotic to titrate to a later equivalent point. And in the case of selectivity, acid-base titrants are not selective, as a strong acid or base titrant will neutralize any base or acid regardless of strength. Okay, so the relative acid or base strength of the analyte and the interferon therefore determines selectivity. Right. Okay, about time, cost, and equipment. Acid-base titration require less time than most gravimetric methods, but more time than many instrumental methods of analysis, particularly when analyzing many samples. So with the availability of instrument for automated titration, analysis time become less of a problem. For example, just now, we know that we can use auto titrator for more easy titration technique. Okay, and for titration manually, the equipment namely the burette and possibly a pH meter, are not expensive and they are easy to maintain, and instruments for automatic titrations are more expensive but they use less time, okay, to complete your analysis. So that is all about learning unit 4, acid and base titration. So I hope you can complete all the study questions and activities for this learning unit and watch all the videos for calculation, back titration. And if you have any questions, you can contact me. Thank you very much.